Welcome back again. In part 2, we used the PDF of the standard deviations to determine the Gaussian functions that we need to sum to create the student's t-distribution. Like this. So now, we're ready to sum them up and see if the result approximates the student's t. Are you ready? On the left side, we'll run through the probabilities of having various underlying standard deviations, exactly like we did before. On the right side, we'll add up the corresponding weighted Gaussian distributions at the same time. So here's our first Gaussian. Not too much to see since the probability is so small. So let's move on to the second one. Our first significant contribution to the final PDF. Here, we see a Gaussian distribution centered at 55.3 watts with a standard deviation of 66 watts and an area of 2.2%. The third Gaussian, the solid green curve, is much larger with a 10.1% probability. We're now accounting for the 10.1% possibility of being in the 40 to 60% range of our underlying standard deviation. We add that to our previous running total, the dotted red curve, to obtain our new running total, the solid red curve. Let's now finish the job by adding in the remaining 7 areas. We'll start out by rescaling the axes on the right graph to give ourselves room. Okay, here goes. So that should be it, right? Let's now compare this distribution against the correct student's t-distribution, the blue curve. They don't match up at all. And I'll tell you right now that the blue curve here is correct. The sage told me so. Okay, let's change the axes so that we can see everything. Alright, time for a confession. I purposely left you with a little mystery to solve, if you didn't notice something fishy already. To keep you on your toes and perhaps wake you up a bit, I neglected to do one thing. Can you figure out what it is? It's a bit subtle, but it's worth taking some time to review things. You'll learn a lot by trying to work through this. Start from the beginning. Think about the steps we took. Look at this estimated distribution and see if it even makes sense. Okay, a hint. These two distributions actually have identical shapes. The only difference is that one is more spread out than the other, so we're on the right track. But what would cause that? What might we have done incorrectly? Okay, there's several tricks I like to use in situations like this. In this case, let's look at a more extreme case to make certain things more obvious. So, let's suppose that we're doing this with 1,000 bulbs in our sample set instead of just 6. Then, the distribution of measured per bulb standard deviation should be much tighter around 10 watts, or 100%. So, overall, our measured per bulb standard deviation should be quite close to our underlying per bulb standard deviation. Here, we see the distribution with 6 bulbs. As you can see, it's pretty wide. But now watch. Watch how things tighten up as we increase to 1,000 bulbs. An extreme case. Remember that our measured standard deviation is derived from random measurements. Again, if we're measuring the standard deviation across 1,000 Brighty bulbs, then the bulbs that are atypically far from the mean, in other words those making the standard deviation high, will tend to be cancelled out by those close to the mean. As a result, our overall calculated per bulb standard deviation will tend to be closer to the underlying per bulb standard deviation. Remember, our certainty always improves when we get to use more samples. Here's that little clip again. Can you see where this distribution is headed as the number of bulbs heads towards infinity? Clearly, the measured per bulb standard deviation, on average, will get closer and closer to our underlying per bulb standard deviation. With 1,000 Brighty bulbs, we would know that our underlying per bulb standard deviation is quite close to 10 watts. So, As the number of bulbs goes to infinity, we are more and more justified in using our measured per bulb standard deviation, which will be close to 10 watts, as the true underlying standard deviation. Obviously, our measured mean will also be close to 60 watts. So, with a huge number of bulbs, our distribution would look like this. Right? Wrong again! We're talking about measuring a huge number of brighty bulbs here. Clearly, we shouldn't have so much uncertainty in our underlying per bulb average power. What haven't I done? Okay, here's the answer. The issue is that I continue to use the per bulb standard deviation, even though I'm taking the measured average as the average of many bulbs. And the standard deviation of this average is much lower than the standard deviation of each bulb. Remember that high and low values tend to cancel out when we take an average. So now, if I used 1,000 bulbs to accurately compute the standard deviation, but only used one 60-watt bulb to estimate the underlying power, then this distribution would be correct. It would be correct because I only used one of the 1,000 bulbs to nail down the average underlying power. But, of course, we're not going to ignore the other 999 bulbs and only use them to estimate the standard deviation. Instead, we use all 1,000 bulbs to create a measured average as well. A measured average that will have much less standard deviation than that of a single measured bulb. So, I used 1,000 bulbs, an extreme case, to drive home a point. With our 6 actual bulbs, however, we're doing the same basic thing. We're taking our measured average from 6 bulbs, not 1 bulb. Therefore, we shouldn't be looking at the per bulb standard deviation distribution. Instead, we should be looking at the standard deviation distribution of 6 bulb averages, since we used a 6 bulb average. And it turns out that that distribution will be the square root of 6 times tighter. So, previously we used the per bulb measured standard deviation of 19.8 watts. And computed all our Gaussian functions relative to that. Instead, we'll now use the inferred standard deviation of the 6 bulb average, or 19.8 divided by the square root of 6, or 8.1 watts. This will make all of the Gaussians that we sum together the square root of 6 times tighter, which will make our final PDF the square root of 6 times tighter. Let's run the animation again with these tighter Gaussians. And this time, we'll start off with the official student's t-distribution, the dotted blue curve on the right. Let's start summing the new, skinnier Gaussian PDFs now. We'll stop at the second region, which goes from 20 to 40%. Once again, this will be approximated as 30%, and will compute the corresponding underlying standard deviation for this region. Notice how we're using 8.1 watts in the formula here, the inferred standard deviation of our 6 bulb average. It's also interesting to observe how this high standard deviation Gaussian, and our next one, pretty much fill in the tails of our final distribution. Now, let's continue until we reach the 8th region. At this point, we only have 2 low variance Gaussians left, and notice how they fill in the center of the curve. So, it looks like we have a good match, but looks can be a bit deceiving. Here's a plot showing the percentage error in our probability density. There's actually a 25% error in our tails. We just didn't see it before because our tails are so low down. But remember that we only use 10 regions, from 0 to 200% to approximate things. If instead we use 1,500 regions and go out to 300% of the underlying standard deviation, our error reduces to this. Nice. Less than 3/1000% everywhere. So this clearly works. Hopefully, All that, including the deviation drama I threw in at the end, gives you a better feel for what's going on behind the curtains of the student's t distribution. In the final section, we'll use this recipe for creating the student's t to make a few observations. We'll also use our Brighty Bulb simulator to confirm that the student's t distribution really works.